Imagine a global internet postal service so massive it could literally support colonies on Mars. Welcome to The Explainer. I am absolutely thrilled to jump into this with you today. We're talking about a drastic, totally necessary upgrade to our digital infrastructure. This system is so incredibly scalable, it's going to easily handle the Internet of Things, your entire smart home, and honestly, way beyond. So let's get right to it and unpack the fascinating world of IPv6 addressing and subnetting. So let's kick things off with a pretty serious question. What actually happens when the internet literally runs out of space? I mean, just imagine a city where no new houses can be built, simply because there are absolutely no more street addresses to hand out. Back in the 1990s, as the internet was absolutely exploding in popularity, we realized we were staring down a massive crisis. The old system, IPv4, was running out of IP addresses. If every new computer, server, and phone needed a unique public address, the whole digital world was about to slam right into a brick wall. Now, back in 1980, the original rules for IPv4 gave us a few billion addresses. And at the time, that seemed like plenty. But by the 90s, the warning bells were definitely ringing. Clever engineers rushed in with short-term patches, things like network address translation, or NAT, and CIDR. These essentially allowed multiple devices to hide behind just a single public address. And those band-aids? They actually deferred the crisis for a couple of decades. But eventually, the well ran completely dry. In 2015, the American Registry for Internet Numbers handed out its very last block of IPv4 addresses. The internet desperately needed a real permanent solution. And here is that permanent solution. IPv6 doesn't just give us a few more addresses to play with, it upgrades the address structure from 32 bits to an unbelievable 128 bits. To put that into perspective, that gives us 10 to the 28th power times more addresses than IPv4. That is enough to give trillions of IP addresses to every single person on Earth, with plenty left over. The whole address shortage problem officially solved for generations to come. But wait, with all that newly added space, there's a bit of a catch. When you put these two systems side by side, the contrast is honestly wild. On one hand, we've got the cozy, familiar IPv4 format, just 4 small decimal numbers separated by dots. Easy, right? On the other hand, we have the new reality, IPv6. It is a terrifying 32-digit hexadecimal behemoth. It's broken up into 8 groups of 4 characters separated by colons, using numbers 0 through 9 and letters A through F. It's incredibly powerful, sure, but let's be real, it looks like an absolute nightmare to deal with on a daily basis. Which naturally brings up the obvious question. Who on earth wants to type out 32 hex digits every single time they configure a router or troubleshoot a network? Nobody. If you're feeling a little intimidated right now, trust me, you are not alone. Luckily, the designers of IPv6 felt the exact same way. They didn't want to type all those digits either. So they built an incredibly clever system to shrink these massive addresses down. You're probably wondering, what's the trick? Think of these as your official IPv6 cheat codes. There are 2 primary rules you need to know to abbreviate any IPv6 address. Step 1. Inside any quartet of 4 hex digits, you can just completely remove the leading zeros. So 0001 simply becomes 1. Step 2 is even better. If you have a string of 2 or more consecutive quartets that are all zeros, you can replace that entire sequence with a double colon. But listen, this is an absolutely crucial catch. You can only use that double colon trick once per address. If you use it twice, the computer wouldn't know exactly how many zeros to put back in each spot. When you apply those 2 simple rules, an unwieldy, massive string of characters instantly shrinks down into something totally manageable. A giant block of zeros just collapses, giving you something like FV80:0:0:1:XX56. This is exactly how you'll see addresses listed when you're actually looking at router configurations or device settings in the real world. It literally turns a behemoth into a total breeze. Okay, so abbreviation solves the human problem of having to type them out. But now we have to ask a much deeper question. With such massive 128-bit addresses, how does the internet's actual hardware sort them? How do routers efficiently divide and conquer this enormous address space without just getting completely overwhelmed? Well, that brings us to the elegant logic of IPv6 subnetting. Just like the old IPv4, these addresses aren't just random strings of numbers. Your public internet-facing address is split neatly into 3 very specific jobs. First up is the global routing prefix, which is usually assigned by your internet service provider. Next is the subnet ID, which your local network engineer controls to organize the internal network. And finally, there's the interface ID, which identifies the specific device. Because the address space is so unfathomably huge, engineers almost always use a /64 prefix length. That just slices the 128 bits perfectly right down the middle. It really helps to think of it like a highly efficient postal service. The global routing prefix, that's like the state and city on an envelope. It gets the packet from across the world to your exact company building. The subnet ID is like the specific neighborhood, or maybe the specific department floor. It gets the packet to the right local network area. And the interface ID, that's the exact house number or desk. It's the specific laptop, phone, or server that the data was meant for. It's just a beautifully organized system. But seeing this structure kind of makes you wonder, does every single device actually need a globally public address? Think about it. A wireless printer in your office or a smart light bulb in your kitchen. They definitely need to talk to the local network, sure, but do they really need to be visible to the entire global internet? The answer is a resounding no. And that's exactly why IPv6 has different flavors of addresses. And the best part is you can instantly recognize them just by looking at their first few hex digits. Global unicast addresses are your public ones, and they start with a 2 or a 3. But for private networks, you'll see unique local addresses starting with FD, perfect for devices that don't need the outside internet. Then there are link local addresses starting with FE80, which are strictly for devices communicating on a single physical link. Finally, if you need to broadcast a message to a specific group of devices all at once, you use multicast addresses, which start with FF. Now here is where things get genuinely magical. In the old days, you either typed an IP address in manually or a central DHCP server handed one out. But with IPv6, you can literally plug a device in, and it can invent its own globally unique IP address without asking a server for help. Seriously, how is that even mathematically possible without two devices accidentally picking the exact same address? Well, it's possible because of a brilliant micro-mystery called the EUI64 process. You see, every network card in the world already has a physically burned-in, totally unique MAC address. IPv6 just takes advantage of that existing hardware. Step 1, it splits that 6-byte MAC address right down the middle. Step 2, it jams the hex digits FFFE right into that gap. Step 3, it performs a little binary trick and inverts the 7th bit of the first byte. And just like that, a physical MAC address is mathematically stretched into a completely unique 64-bit interface ID. Boom, no server required. When you step back, all of this, the hex numbers, the cheat codes, the EUI64 math, it all exists to serve physical reality. The server racks, the miles of cables, the blinking lights on the routers. IPv6 takes the sheer physical mess of connecting billions of devices and applies a perfectly logical, massively scalable subnetting structure to it. It ensures that traffic flows efficiently across the globe without ever running into a dead end. So the absolute crucial takeaway from this explainer is that IPv6 didn't just patch a problem, it blew the doors completely wide open. We have officially moved from a cramped internet struggling for space to a boundless digital frontier. With a system that can literally provide trillions of addresses per person, the limitation is no longer the technology, it's our imagination. The Intergalactic Postal Service is up and running. The only question left is, what will you connect next?